Well, as you do, if you can recall last week we were discussing uh conductor, wire, and conductors, and this topic is a continuation of that topic. So today we're talking about conductors, sizing conductors. Now, if you notice that if you watch the series, the video I sent, let me just put the material here so we can know what we're talking about. Uh, all right. Now, these are what you did what you went through terminology, they determine the maximum current for PV system sockets, defining continuous duty as applied to PV system socket. We went on to identify and describe considerations for selecting conductors to meet ampacity and voltage drop requirements. So with the choice of wire size for PV source sockets and inverter output sockets. That's exactly what this whole material is about. This whole sections is about choosing the appropriate sockets and taking into consideration a lot of things when it comes to choosing your sockets. Do you guys have any question from the video before I proceed with the training section?
For me, I saw 50 particular and put that inverter.
Okay.
And then I saw it that putting the first inverter on the second inverter, the used inverter on the system. I put the first one on, the second one was loading, and you're saying that after the first one go up, the second one, for the steam to go out, the steam the second one will pick up from there. I want to ask if you can use put inverter on the system on the steam system for 1 day.
If we can use two inverter on the same system on one system?
Yeah.
Yes, you can. You can actually you can tomorrow. Hopefully, we have a guy coming in. Tomorrow training. His name is Mohammed. He lives in Liberia. I don't know if you on the group chat. You see some of the videos, some of the project he have done. Huh?
Sorry.
He's gonna be in class tomorrow. He's coming back tomorrow to talk to you guys. So you guys can ask him any question you got from that video section. He's gonna be, he's gonna be part of our technical team. He's a veteran in this whole area. He's a good electrician, and he's doing tons of solar renewable energy jobs. This guy is great. He actually even know about wind turbine, and so forth. So it's good to have him on our team. I would love for him to come and meet the team. Mr. Kotuma, you have any other shirts? How many shirts Roman gave you? Prince gave you?
7 pieces.
Or he gave you 7 shirts. So you disperse 4. So you have 3 more.
We have this bronze 5. So 2 more is there. One for Ghana.
One for who? Oh, the other Lincoln? Okay.
One left.
All right. Okay. But it's fine with print more. But you guys like the shirt, not so?
Yeah.
Okay, great. Stand in front of the camera. Let me see your shirt because I think the shirt. Hold on. Somebody stand in the camera. Let me see the shirt print. Okay. Yeah. Okay. So let me see your print. And it's fit well, isn't it?
Yeah.
We had different sizes, Mr. Kotuma.
Yeah, we have 2 different sizes. More than that.
Yeah, I personally, I was trying to do something like, I know you can see my print on my shirt here, but he said in Liberia it's more preferable that people can see the design on the shirt. So according to him, that's why more company does, even he who work with Orange, that's what they do. They print the design on the shirt vividly so people can see it. And even our girls on the field, I noticed that they have the same shirt as well. Um, uh, we wanted Lincoln to be able to, let me say, uh, Roberto to be part of the follow-up team, but apparently that area now is not working well. They got a series of numbers and people are making calls. But I understand Mr. Kotuma lost his phone, and that is your phone number on that flyer, isn't it?
Yeah, yes. So,
So they have the database of customers that need to be called. So we gotta talk about that later after this class. Okay, you can have a seat, guys. Have a seat.
no, it's active. Yeah. That number is active.
Oh, it's active.
It's not care about number.
Oh, okay, okay. All right, great. So all right, guys, let's dive into this training. Let's go right in there. I'm gonna share my screen. So, all right, I will start with this. I will summarize what you guys read through. We're talking about sockets and conductor. Conductor sizes, sizing conductors.
Excuse that.
Uh-huh.
You ask question, we will still trying to ask our question. Through the video that we watch
Yeah.
concerning the connection, I saw two different connections with the macro inverter and the macro converter.
Mm-hmm.
Yeah, we have macro inverter on the PV. Then on the other side, we saw the macro converter, but it's from DC to DC. We have converter. Yeah, DC to DC converter.
Mm-hmm.
We have the inverter that from DC to AC, we have inverter, macro inverter. From DC to AC. From DC to DC, we have converters.
Okay.
So inverter and converter. What is the inverter and converter?
All right, we will go through that. Let me run. I think I have to run through that.
Yeah, and the next thing I noticed that the connection of the PV in parallel in series.
Uh-huh.
The parallel connection from the let's say when they use the macro inverter, it's everything in parallel.
Mm-hmm.
All the PV that have macro inverter, they're all in parallel.
Yeah.
Yeah. Yeah. And it's better. I'm serious. And what do you come across it?
Okay, I will go through it. I will give you the source. I will go through that. So let me just run through that. Let me run through what you guys have read through up to 10. All right, so here we're talking about, let's start from here. At the completion of this lesson, students should be able to identify terminologies for the various sockets in PV systems, determine maximum current for PV system sockets, define continuous duty as applied to PV system sockets, identify and describe considerations for selecting conductors to meet amplicity and voltage drop requirements, choose wire size for PV source sockets and inverter output sockets. So this is exactly what you should be able to be familiar with at the end of this training section. If you look at this diagram here, this schematic, this diagram shows the PV in series. We have a PV in series of 5, 1, 2, 3, 1, 2, 3, 4, 5, 6, 6, I mean. So we have 24 models in total. The 24 models are divided in 4 series. You have series number 1 has 6, number 2, number 3, number 4. Now, when you notice that these series are paired, you notice about positive to negative, positive to negative. The positive from the first model goes to the negative of the second model. That is how they are paired in series. Now, then you have, in parallel, you have this first negative, which is this negative. You see the negative, the black line going to the conjunction box. Are you seeing that?
Yeah.
Then you see the positive also going to the combiner box. So you combine the panels in series and you run the parallel. These are the parallel connections. It is a parallel connections from the end of both series that goes to the combiner box. But today we are just discussing conductor sizing. So I don't want to go depth into a didn't we do a topic on parallel on parallel and series? We did a course on parallel and series, didn't we? Okay, so we gotta go. I gotta go. Okay, I gotta do. There's a course on parallel and series, knowing what connections. But uh, oh, that okay. So that was on the bypass sizing. All right, great. Thank you for that update. Now, if you notice that, so what they're saying here is these are conductors. These are, sockets. You have a socket, four source socket. There are four sources of sockets here. We have the socket. If you notice that there is a socket that combine all of these going to this combiner box is a socket. Going to the disconnect, there's a socket. Going to from the inverter, going to the AC connect, there is a socket. You notice where the sockets are. So the sockets are here. We have one socket here. The combination of these conductors, and we have one socket, two sockets, three sockets, and four sockets. Can you see that?
Yes.
Okay. Now, I think I got to read this before you guys understand it. The National Electrical Code NEC defines PV source sockets as socket between models and from models to the common connections point of the DC systems. The NEC 690.2. Many installers use the term series strings, which is another name for PV source sockets. In this schematic, the common connections between common connection point is the combiner. The connection point is the combiner box, meaning each of the socket between the models and the DC combiner box are PV source socket. Do you understand that reading?
Yes.
So they're saying the connection between the models and the combiner. This is a socket right here. There is one socket here. There's two socket in this combiner box. We have a socket connecting all of these models to the combiner box. Did you understand that?
Yes.
I'm gonna go back to explain. Lincoln,
Yes.
you are an electrician, are you?
So it's not another different,
Oh, it's the other Lincoln. Okay, excellent. All right. So what we are saying here, that's why tomorrow I'm going to have somebody physically physically on the ground to practicalize these things. They're saying here is you have sockets. These are conductors. Don't confuse conductor for sockets. We discussed conductors in our previous lesson last week. This is a socket. Socket is the junctions between these connections. That's the socket. You have a socket in the combiner box. You got a socket in the disconnect. You got a socket inverter. You have a socket in the DC connect, and you have a socket going to the AC panel. Those are the sockets. Do we understand it? These are conductors. Do not confuse conductor from sockets. We talked about conductor last week. Remember, we talked about the different types of conductor and kind of conductors? Okay. So we're not talking about the conductor. These are PV conductors. We're not talking about the conductors here. We're talking about the sockets. Is that clear? Or are you guys baffled in that area, or you want us to go over it again? I think when we continue, you guys will get it further. Let me see. I think. Huh? You want to ask question here? Okay, go ahead. I think you guys too far from the speaker because I'm not hearing you guys. You guys too far from the system. I'm not you're too far. For some reason, you're not.
I said,
Yes, good.
I've always seen the combining box. I want to know the DC that DC disconnect. Where for the connection?
Okay, the DC disconnect is like a breaker. You know, like a breaker in the house. So the DC disconnect disconnects the entire DC system. So all these model here sending in the DC current or the DC current coming into the combiner box. Now from the combiner box here, we don't want all this current to not be restricted. So for example, if I have to work on my model up here, all I'll have to do is shut off this disconnect. You got it? So you can shut off the disconnect. It disconnects the DC from the AC. So if a technician is working on the AC section of this system, they can shut off the disconnect, almost like a valve. You know, like you have a water valve, a water valve. So if you have a water pipe, let's say in your house, you have water pipes, okay, and they have a valve on the water line. You can, if a plumber want to go work in the bathroom, he goes outside or he shut off the valve. So he closed the valve of the water. He closed the valve so that to prevent water from coming in while he's working. So that's the same old way here. This here prevents the the current from the DC installation from the array from coming in to the inverter. We will talk about that later, but let's focus on what we're discussing today. Okay? There is another topic for those devices like disconnect, the inverter, and so forth. But for now, I want to drive on that. Now, if that is not that clear, let me see. I can find something right here. I'm gonna find something where I can just practicalize that for you. Hold on 1 second for me. Come. All right, guys, let me go because it's a long. If I want to talk about this, connect will be too long. So let's proceed. But just bear in mind that the purpose for the disconnect is to avoid. Eh?
To break between the DC for power to enter the inverter.
Yeah.
Yeah, so instead of whatever for the power to not enter the inverter, you want to break the inverter side, power should not come for the PV side of the inverter. I understand what you're saying.
Okay, let me just go over this quickly. Okay. If I'm doing a installation of this system on the roof, I mounted all of my models. I did all my series connections in four different series. I run all of my parallel cables to my DC combiner box. Okay?
Yeah.
All these cables are connected to my DC combiner box. There is absolutely automatically this panel, as the sun start hitting this panel here, it start generating current. You got it, Mr. Fatuma?
Yes.
It start generating current right away. So I'm working in the day, and I already mounted my panel. I connected all of my my sockets to my DC combiner box. They are automatically sending out current. That's why I need a DC disconnect. So the DC disconnect will stop. You see the pin over here looking like a pin?
Yeah.
All right. So if you see over here, there's something like a little pin. You see that little pin?
Yeah.
So that pin now is down. The breaker is down, or the switch is down. If I switch it up, this pin here will hit this two connection. When it hits this two connection, automatically the current from my combiner box begin to run into my cable. So I'll shut this off so I can be able to properly install my inverter and install all of this section of my installation. You got it, Mr. Kotuma?
Yes. Yes. Yeah.
So that's the reason why you have that DC disconnect. It's important to have a DC disconnect on a system as big as this. If you don't have a DC disconnect, once you run from the DC combiner box, you run your cable into the inverter, automatically the current changes into AC current. When it changes to AC current, it's sending a current directly into the house. So whatever appliances you got on or something not right, automatically it start causing trouble. You're not supposed to do that. When you do installation, you gotta go step by step. You mount your model, you do your series and parallel connections, run it to your combiner box. For the combiner box, you have to have a DC disconnect. Okay?
Yeah.
So the DC disconnect is actually it's for safety as well. So let's say there is a problem, there's a problem with the models up there. There's an issue. If I don't have any means of shutting this system off, what's gonna happen? That current will run directly into the house. But if I have a DC disconnect, I can run and shut the DC disconnect. Or a DC disconnect, sometimes they have a switch that when certain things happen, it will automatically fluctuate. So that's why you need a DC disconnect. Very important part of your installation process. All right?
Okay.
Okay. So let's move forward. You guys got a copy of your material now?
Thank you.
Francis,
Yeah,
you printed a copy of the materials now?
yeah.
Yes.
So you guys have,
Everybody get a copy.
Everybody get a copy.
okay, so you have hard copy of this one here as well?
Yeah.
Okay. Now, okay, I just read for that. Let me move to the second one. Now over here, this second schematic here, this second diagram shows something called a macro inverter. Macro inverter is not very popular, especially in Liberia. I don't think it's not popular in Liberia. Macro inverter is expensive, but it's beautiful. But one of the advantages of having macro inverter is that the way you see here in this schematic here, we have a series of 4 different strings. If anything happens to one of this panel or this model, it affects the entire string. You got it? So for example, let's say there is a shading. Shading could be maybe the tree shallow, or maybe a dust or something covers this model here. As this model loses power, it affects the entire series. But unlike the inverter, if you have a macro inverter, all of these models become independent. So if anything happens to this model here, for any technical reason, if something happened to this model, say the model here, something happened technically, it got broken or it's not receiving current, and now you're getting good sunlight, it's not going to affect the entire series. That's one of the beautiful a beautiful advantage of a microinverter. Now, also the microinverter, what it does is that it changes right from the roof. It changes the current from DC to AC. Look, right from the roof, it changes the current from DC to AC. So right on the roof, if you connect your microinverter to every model here, these model now, they all change. All the current that comes from here now become AC current from the roof. That is why you have your parallel connections coming over to your junction box. You notice that in this connection here, we do not have a compounder box. We have something called what? A junction box. Do you notice that?
Yes.
So it comes, so you have the connection going into your junction box. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 20 model in a series of 10. So they are all connected here by series, negative, negative, positive, negative, positive. But then the cable that runs that runs through the inverters is all parallel. That's the question Mr. Kotuma was asking. Not so, Mr. Kotuma?
Yes.
So this is a parallel connection coming down. Parallel connection coming down here. How many sockets we have here? Do we have one socket? Two sockets? Three sockets? How many sockets? We have one socket here. We have two sockets. We have three sockets. One socket from your models to your junction box. Another socket from your junction box to your AC compounder panel. From your AC compounder panel to your AC disconnect, you have another socket. Is that clear? Any question?
Proceed.
So you notice that this is a great direct system. We don't have no battery bank here, so we don't have no 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 charger. We don't have no charger here. There's no charger in this setup. Because why? The way the system works, this AC panel receives current from the meter. So there's a meter. The meter from maybe LEC or Firestone current is also coming into this box right here. So Firestone also sending current into this box right here. That is why you have the AC disconnect. The reason why we have our AC disconnect is that in case we are about to use our current that comes from the DC part of our installation, the AC disconnect will disconnect the system. Are you guys hearing me?
So we have one.
I'm going to go through it again. If I want to work on this side of this system here, this is a AC service panel. In Liberia, you call it your breaker. You have your breaker box in the house. So this red cable here indicates that you are receiving this cable. These are the connection from the grill, from your meter, which means you have LEC current. So this whole system here, when LEC current shut off, your solar panel provide you current. When LEC current comes on, your solar panel shut off. You got it?
Yeah.
Okay, so that's how it works. So, and secondly, for developed countries, you actually the meter can read backward. So what it means is that you will be able to sell power to the grill. When your meter read backward in the day when the sun is shining and you're getting more power, you can sell to the grill. I mean, your meter read backward. Instead of your bill is $100, it start going back from 100, go all the way down. But then when the sun goes down, the meter begin to read forward. So all through the night, you'll be using you'll be using LEC current in the day, when the sun is up, you'll be using your DC system. But don't worry much about that section because this kind of setup doesn't work in Liberia much because we don't have a good grill system. We don't have a good LEC system. Uh-huh.
I think they are working on LEC. In Toronto, they have plenty of posts on LEC. So eventually, we'll have application for this.
Yeah.
Oh, okay. They're putting posts there.
Yeah.
Oh, lovely. That's nice. That's beautiful. So we're gonna have lights. Did they put the same solar panel lipo now on the streets?
Well, the post, they are still putting the post. No, from Monrovia to the street light, yes, you have to city.
Yeah, we sent one of those lights to the school over there. You guys gotta go and install it.
Yeah.
I sent one of those lights to the school. So I think maybe when Mohammed comes tomorrow, I'll ask him if he can go down there also. Maybe you can go down and see the installation, the setup of that light.
All right. The rest of the materials for the installation. The nothing wrap is better, the wires.
It doesn't need that. It doesn't need the street light. Don't need all of that. It's just it's a street light already set. It has everything. Just a light. It's just gonna mount on the roof on the roof. It has everything on it. I'm not talking about the PV. I'm talking about the solar system installation because the lady said it's better she wait till I come. But they're going to use the light is for them to do it out there. So when the girls when they get dark, they can sit outside if they want to still be around the school. Yeah, so Prince brought that. So we got one of those. Actually, one gentleman like in Morovia, I had to get him one, and he installed it over the house. It's doing it works very nice. So let's move back. Now we have our sockets here. These are our sockets. We have one socket, two, and we have three sockets on this system right here. This diagram shows an example of a microinverter system. By definitions, source sockets are sockets between models and from models to the common connection points of the DC system. So the PV source sockets in the microinverter systems are the model lead, which connect to the microinverters. These model leads are the only DC wires in a microinverter system. Looking at the definition of PV output sockets, socket conductors between the PV source sockets and the inverter or DC utilization equipments, the model leads could also fit these descriptions, since they are located between the source model and the inverter equipment. However, they are commonly just referred to as source sockets, since they are not combined. The inverter output socket is defined as conductors connected to the AC output of an inverter. In this diagram, there are two inverter output sockets, one from each branch, socket of 10 models inverted, 10 models slash inverters, running through a junction box for an AC combiner panel. The output of those first two inverters output sockets are combined together in the AC combiner panel, and the resulting output socket is also called an inverter output socket. In fact, the entire socket between the AC combiner panels to the point of the interconnections will be called an inverter output socket, regardless of what kind of equipment may be included, such as meters or disconnect, and it may consist of several different wire sizes. So that reading is very clear that these are all sockets. You got it? You got it now? You understand it? So these are your sockets. These are your conductors. That's why we discuss conductors before we talk about the sockets. So don't confuse conductor and sockets. This is a PV. This wire, this black wire here is a PV conductor. But when this PV conductor comes in here as a group, they become a socket.
I think you get
Mm-hmm.
So in running these wires, someone said it as we said it in the previous lesson.
Mm-hmm.
You have to run this wire through the conduits, right?
Mm-hmm.
Where it's applicable, running through the conduit.
Mm-hmm.
But the converter are there and the conduits are there. So it's any application you need conduit, you can't run it directly on the bare wall.
No.
Yeah, okay.
Mm-hmm. Now, this is what you were asking about. You were asking about the DC to DC disconnect, were you?
Yeah, and also the converter there.
Okay. So first and foremost, I have to tell you size and DC disconnect for a student. I have to first tell you what a DC disconnect is first. This is talking about the whole system. I just want to just first let you know. All right. So a DC disconnect, you can see this, but a DC disconnect are switches that complete or interrupt the flow of DC electricity in the solar PV system. The DC disconnect is placed between the solar panel array and the power inverter, so it is easily so it can easily be thrown if you or the fire department need to shut off the solar panel system. So that's why it is. But what we want to know about this converter output, DC to DC converter. Is that what you want to know about? The DC to DC converter. Where's my so small? Hold on, let me see the view. Okay, nice. So the DC to DC converter, what it does is that it is enable the solar panel to maximize to be able to get the maximum current from in the panel. For you to be able to get in the maximum, so you can have less of a loss. You can have the maximum current from in the model. The DC to DC converter is used. So regularly, when you install a panel, I mean, it's going to get you're going to get current from there. But if you want to get the max, you want to get the max of current from that module, you have to attach a DC to DC converter. So all it does is that it just draw more. It gives the model the ability to perform more. You get more current. So say for example, you were getting say you were getting you were getting 48. You were getting, I know how to say it easily, but because there's no way to measure the exact amount of current. But what it does, just taking the note that it enables the model to perform greatly. It sucks more current. That's what it does. That's what it does. So it give it a prep. I'm sure I got material on that we're going to be discussing further. But when we start discussing different stuff, we definitely will. But for now, that's exactly all I can really discuss. So I can actually discuss right now. So because I don't want to take all my time. I got this material is long. It's a very long material, and I don't. I, we have not. We are just page 10, and it's all the way to page 27. So we need to go through a lot. Okay. Say right here, DC to DC converter provide capability to either step up or step down a fixed DC voltage source. The converter can not only be used in devices such as an automobile as power supply, but they can be used to. So it's NMDC sources, even in car, even in automobile that it has 12-volt power, they has DC to DC converter. Do you got it?
Yeah.
All right. I am prepped up to run that material through. So I want to go there because we have a lot to do. So if you look right here, the more idea I want you to grasp from this concept is what the sockets are. There are two DC to DC converter output sockets, 16 PV source sockets. So we have 16 PV source socket here, and we have two DC to DC converter output socket. What they are saying here, each of these models individually has a DC to DC converter. But then when we combine them all, we have this running to the junction box, and we have another running to the junction box. So we have only two sockets. Even though there are 16 of them, after we got done with our connections, our DC to DC connection of our models, we only send two sockets to the junction box. Two sockets going to the junction box. And you notice that the runs here, the runs that goes from here, from the model to the junction box, we have one negative going there to the junction box, and we have one positive going to the junction box. From the first set, we also have another negative, and we have another positive going to the junction box. So that makes it two. So we have two sockets. Even though we have 16 models, but we only have two sockets runs. If you notice from the inverter, this is an inverter. This is called a solar edge inverter. From your inverter here to your DC disconnect, there is another socket called your inverter socket. We have an inverter socket here, which runs to your disconnect, the AC disconnect, and to your AC service panel. I'm going to read a little bit about it. All right, let me read about it a little bit. The diagram shows an example of a DC to DC converter system. DC to DC converter source socket and DC to DC converter output socket are separately and individually defined in the NEC. What the definition of NEC?
National
Electrical.
The National Electrical Code. Okay. DC to DC converter source sockets are defined as sockets between the DC to DC converters and from DC to DC converters to the common connections points of the DC system. In this system example, the two sockets from each string of series connection converters fit this definition. since they are from DC to DC converter to the common DC connection point, which happen to be inside the inverter. However, they also fits the definition of DC to DC converter output sockets. It does not really matter so long as the correct level of current in the socket is used, as the rules are essentially the same for both. DC to DC converter output socket are defined as socket connector between the DC to DC converter source socket and the inverters or the DC utilization equipment. In this case, we will call the two sockets from each series string DC to DC converter output socket, since each is carrying the combined output of all the converter for that string. The model lead in this case are considered PV source sockets, even though they are part of DC to DC converter system. The inverter output socket is shown here between the inverter and the point of interconnections in the AC service panel. Sizing conductors for PV system. Conductor size considerations. Conductor amplicity, the NEC requirements to ensure safety, voltage drop, the requirements for good system design to ensure maximum system productions, and the proper operations. Too much voltage drop can lead to what? Reduced productions and system not operating. There are two primary considerations when determining an appropriate conductor size. One, the amplicity. Two, the voltage drop. These will be discussed in more detail in the following slide. So all I just read about is considering the conductor amplicity, the voltage drop. These are very important when it comes to sizing conductor. Taking into consideration voltage drop. It's very important because if you have too much voltage drop, you will reduce your production and your system will not operate appropriately, will not work. So that's why conductor sizing is very important. You can install your model up the roof, you put it in the nice way. When people look at it, it looks so beautiful on the roof. But if you don't have the appropriate or you don't do the right connection when it comes to your conductor, you're going to have a problem. You're going to have a problem. So this is a very important aspect of this training. And the good thing is, some of you guys are going to be able to see some of the job that Mohammed does, and y'all be able to see this practicalized, seeing it done practically. The good thing when you have the theoretical skills, once you see it practically, your mind will automatically light up. That's one thing about learning. Once you see this practically, your mind will kick off. Oh, this is what we talk about in class. You know that? Your mind will automatically light up. So let me continue. Let me see what page I am. I want to move forward. I'm talking about digital. Now let's go down to inverter output socket size considerations. Now they have the National Electrical Code continuous output current readings. Inverter maximum output current. Continual operations, 3+ hours. Temperature and multiple conductor adjustment. Device terminal and capability. Voltage drop. Rates inverter continuous output current. Nominal AC voltage. Socket length. The conductor resistance per foot. Manufacturer limits. Now we say amplicity and volt drop requires much more also be considered for AC socket in a PV system. Inverter manufacturer typically set limits to the amount of voltage drop that can occur. And it always important to read and follow the instruction regarding voltage drop limits. Now, one of the beautiful thing about this whole setup is that every socket, every inverter, or most of these appliances when you read the operational manual or the data sheet, it has information that tells you what you need to know. They'll tell you about the maximum. They'll tell you some of the most important things you need to know when it comes to uh, the rate of a voltage drop. I mean, how much of a voltage, how much. They tell you everything you need to know. So these information are available from the manufacturer. Most manufacturer does. I mean, all. You just have to go and either you have the manual with you, or you have the data sheet, or you go online and research it, or you go on the website and download it. If you know right here, when we continue, I have this is a data sheet for a PV models. This is a data sheet for the Q cells PV model, the one I shipped to you guys. The model we're using for uh for Stanford's job, 390 watts PV model right here. It tells you about the MPP. They tell you the MPP2, the socket drop, the ISC amperes. They tell you everything you need to know. But we're going to go through that gradually, and then you understand it. So these information are available. You just have to get the right resources when you're doing your job. Now, now this is one of the most important places. PV source output sockets maximum current. The PV source and PV output socket maximum current. Environmental conditions can excel STC ratings. Okay, so if the STC ratings was given, they gave you the minimum STC ratings. So if I look right here, they say the short socket, the ISC short circuit is 10.05. That's the minimum. The minimum given here is 10.05. We have to find the maximum. We have to find the maximum so we can know how much of a continuous. So if there's maybe that what they said 3 hours. So let's say the sun went at a higher pit for up to 2 to 3 hours. If that socket or that model can handle that much of a continuous. So these are things you need to put into place when sizing or when installing configuring your model or your installation. Very important. Let me go back to this here. So they gave you the simple mathematical configuration. Maximum PV socket current equals the ISC times 1.25. Write that down, or cycle it in your pamphlet or in your handout. The maximum PV socket current equal the ISC times 1.25, which is the irradiance factors. The maximum current, an amount you could actually measure with a clip-on meter. So clip-on meter can also, the clip-on meter has actually sent some of those tools. Clip-on meter can also be used to measure the maximum current. You clip the clip-on meter on your socket and you press the button. They have the button you press, it will tell you the maximum current of that socket. It's very important tools to have. When we look at the NEC section 69.8, it defines the maximum current. This defines the maximum socket current or maximum current for PV source and output sockets as a sum parallel connection PV model rating short circuit current times 1.25. Number of socket in parallel times ISC times 1.25. How many sockets we have in parallel here? I'm going to go back here. Let me see. So how many in parallel? How many sockets we have in parallel over here? We got 3 sockets in parallel, and also,
Yes.
so that's what they're talking about. You see the sockets in parallel? 1 socket, 2 sockets, 3 sockets. 1 socket, 2 socket, 3 sockets. I want to guys, give me a second.
I wasn't there. It's not really.
Yeah.
All right, guys. All right, look behind this. This is a model. This is the nameplate of a PV model. Can you see it?
Yeah.
This is the nameplate. This is behind the solar panel. This is behind the PV model, and this is the label. This is telling you what is the maximum. Hold on. It tells you what is the maximum socket current. ISC 5.618. It tells you what's the maximum power current. The IP max 5.38. It tells you what's the maximum power voltage. VP max 42.04 volt. The maximum system voltage 600 volt. Do you see that?
Yeah.
So these information you need, they're always available. This is right behind the model. Behind the, if you got Mr. Fatuma, you got a model at your house, don't you?
Yeah.
You go and look at the nameplate on the back of the model. It tells you some of these great information you need. So when you're doing your installation, you know where to find the maximum power. The maximum power here is a 215 watts panel. The short socket here, which is the ISC 5.61. The maximum power current, the maximum power voltage, the maximum system voltage. These information are available. They are there. So for your calculation, that's going to be very helpful for you. Over here it says this is the 69.8A photovoltaic source socket current. This is the code. In previous editions of the NEC, the maximum socket current for PV source socket conductor between the PV module and from modules to the common connection point of the DC system was calculated by taking the short socket current ISC from the module nameplate and multiplying it by 1.25%. All right? The short socket current, the ISC, from the model nameplate and multiplying it by 1.25. Now, I'm going to give you a quick assignment. I have, this is a 100, okay, right here. The short circuit current for this model here is, for, write it down, 380 watts panel, 380 watts. This is beautiful. You write that down?
Yeah.
Okay, for 385 watts, we have 10.10. We have 380, which is 10.05. Then we have 385, which is 10.10. Then we have a model 390, which is 10.14. Then we have a model which is 10.19. These are the short circuit current, which is the minimum. Now we're going to do a math to find the maximum. You wrote that down or wrote them down already?
Yeah.
I don't say you should add everything. I said, right, you wrote them down? I just want you to write the various watts down. The first watts is 380 watts. That's the first model. The second model is 385 model. The first model, the short circuit current, write the word short circuit current, or you can abbreviate it as RSC. The short circuit current amps. Short circuit current amps. You wrote all of them down?
Yeah.
You wrote all of them down?
Yeah.
All right. Now, we're going to find the maximum. These are the minimum. We're going to find the max now. So we're going to multiply 10.05, we're going to multiply it by 125%. 125% when you move the decimal will be 1.25. So you said 10.05 times 125% equals, what did you got? Let me write my own down. I'm gonna write my findings, my answer, so I can tally with you guys. What you got?
5.56.
So your maximum current will be at 12.56, and that is for the 380 watts.
Yeah.
All right, continue. Go to the next. I'm writing that down. So you 12.56, 12.56. You can't say 12.56. You have to round up the next deck, round to the next. So you're going to be what?
12.6.
12.6.
We will say, we'll have one. I got you. Okay. Okay. The first one we have 10.05 times 1.25. We get it 12.6.
Okay.
And the second one, 10.10 times 1.25, we get 12.6 again. But 12.6.
All right.
And the last one, we get 10.14 times 1.25. We have 12.7. The real one is 12.675. Running up to 7. 12.7. 12.7.
Mm-hmm.
That's all right.
Okay. So I want you to do something. I want you to all right, you have all right, hold on one second. What I want to do. So I want you to 10.05. Okay. Now let me go back to my. I'll write this down for you guys. That's the rule of thumb. If you have 10, if you have 10, if you have 10 380 models, you have 10 380 models, and you pair them in series. Now, I want you to add the short circuit current for 10 model, which is 10.05, multiply that by 10.
One 100.5.
What you got?
100.5.
Multiply by 10. Now I want you to multiply that amount by 125%.
will give you 12. They will give you 12,500.6.
They gave you 125.625. That what you got?
Yes.
All right, move the decimal place one place.
They will give you 1,125.6.
Oh, you're moving in one place, not two places. If you move the decimal one place, you will say you will have 12.6.
12.6. One place to the left.
One place to the left. The reason why I asked you guys to do that is if you pair 10 panels in series, the amps remain the same. The voltage will increase, but the amps will remain the same. So if you notice right here, let me go back there. Right in this diagram, they have 10 models here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They have 10 models. Now, all these 10 models here pair in series. We already know that the maximum coverage, we know that the given, we're using this model. Say, for example, we're using this 380 watts panel. We know the short circuit current for the ISC ratings is 10.05. 10.05, even if you have 10 models, you're still going to have the maximum of 12.6. That's not going to change. You got it?
Yes. So,
let me read.
Brother,
yeah.
So the 1.25 is posted for the ISC.
Yes, right here. That's a code. That is the 690.8A. That's a photovoltaic source socket current. That is the NEC code. Say right here, the code change summary, the code chart summary. In previous edition of the NEC, the maximum socket current of PV source socket current, PV source socket. That's why the maximum socket current for PV source socket conductor between the PV models and from the model to the common connection point of the DC system was calculated by taking the short circuit volt current. What is a short circuit current? Right here. This is your short circuit current. Short circuit current, which is what? 10.05. You got it? I'm going to go over it again. I want you guys to, let's do this. I want you guys to, everybody go outside for 5 minutes and come back. Or just take a walk outside, just so your brain can come down a little bit. Just take a stretch outside. Open the door 1 minute or 2 minutes, just so you can regain yourself.
Hello? Hello? Then I'm going to
Hello?
Yeah, we're back.
All right, great.
No, come on. It's not a bad idea. Well, come on. No, onde ele fica bem.
No.
Onde fica a chave.
Reduce the charge?
Bye.
Are you guys ready now?
Yeah, we're back.
Your brain feel a lot better now?
All right. So,
Can you see the screen?
yeah.
All right. I'm going to if I can print this. I'll send this to you guys. I just printed it. Trying to save this. Now, I decided to go back a little bit. We're not going to run through this topic too fast. We can end everything today. We may complete it next tomorrow, but I think what happened is I want to take my time because this is a very crucial area when it comes to the installation of a PV model. Now, the NEC and PV related terminologies. The first thing I want you guys to note is what the definition of those things I'm talking about. There are specific terms used for PV system components and sockets. The NEC differentiates between a PV power source and a PV source socket for PV system. A PV power source is an array of collections of arrays that generate DC power. How many of you know what an array is? Okay, so behind me here, over here, this is an array. It's an array of two models, not so? Okay, if you look right here, there's a little, can you guys see the little picture? All of these PV models combine together. It's called an array. I want to familiarize you guys. All of these models combined together are called an array. So they're saying here is the PV power source. When I talk about power source, they're talking about just the array, or they're talking about just your array. That's where the power comes from. The power from the sun, it hit the array. So let's stick right there. That's the power source. The inverter does not generate power. The combiner box does not generate power. The breaker does not, all those they don't generate power. The only source of power in that system is the PV array. Is that clear?
Yeah.
So if you have a DC system, once you don't have the PV array, you can take that combiner box, your this that you connect everything together, they will never be able to generate power because you don't have a power source. It's like when you have your cell phone. Your cell phone has a power cable. The power cable is a power source on the battery. Your cell phone have a battery, I mean. But the battery need to be charged. In order for the battery to be charged, you have to connect that cell phone to your outlet in the wall or a power source. Not so? So there is a battery in the cell phone, but the battery is not the source of power. The battery is the battery is reserve power. It keep power, then it use that power that is kept, but you have to fuel that battery with power by charging it. So this is the same thing here. So I just want to break it down a little bit. The power source is a PV array, the collection of PV array. That's your power source. Just keep that in one side of your brain. Then we have your PV source sockets, which we're talking about today. That's what we're discussing today. We're discussing the sockets. Is the PV source socket is the socket connecting a group of modules together. Okay? That connects the group of modules together. A group of modules together. And the common connection point of the DC system. The PV source socket are usually a string or series of connected modules. For a small system, the PV power source is usually only one source socket. A larger system, the PV power source is usually composes of several parallel PV source sockets. So let me go back to my material here. This is our array. This is our source of power, this model. We have 20 models here. These are our source of power. Let me leave from there. Let me come right here. This make it easy. All these 24 models are our source of power. I can take all of these models here, build a rack on my roof, install them, and once I do not run this socket here to a combiner box, they will stay here for the next 200 years. They will just be generating current on my roof, but that current will not be utilized. You got it?
Yeah.
I'm gonna have sockets to take that current and bring them into the DC combiner box. From the DC combiner box, I have to have socket to bring come into the DC disconnect. I need socket from the DC disconnect to the DC side of my inverter. That's why you see there's only one socket between here, because the inverter also has a DC side. The inverter has a DC side in here. So that's why they don't put another socket on this side of the inverter. It says right here, the same socket going to DC. This is a DC line going into the DC part of your inverter. But when they're coming out here, there is a socket. There is an AC socket. We have an AC socket here, the AC run, and this is an AC socket. So that is what I'm explaining today. I'm talking about the sockets that is used to run your power from your PV model to your DC combiner box to your DC connector, to your inverter, to your AC disconnect. DC disconnect, your AC disconnect to your AC panel. Is that clear?
Yeah.
You understand it now? You got a baby. The baby is born. The baby is a few months old. When the baby is a few months old, what it does? The only thing baby do when they're a few months old, they just lay down. They can't sit down. They can't stand. Then after then, they learn how to walk. They learn how to sit down first. When they learn how to sit down from there, they learn how to crawl. From crawling, then they learn how to hold something. From holding something now, they start running around. That's the same trend. I'm just giving you a symbolic expression of that's how every system is configured. You cannot start configuring the system from the AC panel to go up to up there, up to your roof. You start configuring the system from up here to come down. Is that clear?
Yeah.
So this AC part in most homes is already established, especially if the person already has current in the home. The AC section is already established going to the AC panel box. That is established. Our job is to bring in our DC connectivities, our DC system into their home. That is our job. Our job is to build a system, a DC system that will provide a DC current that will be inverted into an AC current going into the home. That is our job. So our specialties is with the DC section. As we go along, since we have some technicians that are vibrant in the AC section, say we have to wire a house, we're doing a wiring system for a home, it makes it easier for us because we do both the DC and the AC. Is that clear?
Okay.
All right. All right, that's good. Let me go down. Ooh, so we all understand this configuration we just did. We understand it also?
Yes.
So we all understand how to find the maximum socket current. We understand that now.
Yeah.
Because we know now from the nameplate of the panel, we find the short socket. It tells us the I, it gave us what we call right here. It tells us the ISC ampage from the nameplate. We are already told the ISC ampage of 10.05, 10.10, 10.14, 10.9, and 19. All we're going to do is we're going to multiply that by, let me do this one, 10.110, 10.10. We multiply that by 1.25 equals 12.6. I'm going to go to the other one. 10.14 times 10.14 times 1.25. It gave me, did you notice that it's all the same? It's still 12.6. Do you notice that?
Yes. Even the
You notice that from the 10.05, we were able to round that up to 1.6, then to 12.6.
Yeah.
So all we had to do now, so they become 10.6, we run the number up to the nearest 10, so it becomes 10.7. It's now at. So the 10.10, let's do 10.110 times 1.25 equals 12.6. That can be run out. Do that math. 10.10 times 1.25. You get what? So it's 12.6. All right. Let's do the next one. 10.14 times 1.25 equals. So what would be? It'd be 12.7. All right. Let's do the next one. 10.19 times 1.25 equals. Your answer, let's not take long to it. The answer is 12.7. So the answer is 12.7. That is the answer, 12.7. So we know that. Why you need that information? If I went to go buy a socket, if I'm buying the socket for my job, and my PV model already just told me that the short circuit current for this model that I'm installing is 10.05. And I went to buy my short socket. I decided to go and buy the short sockets. Let me say short socket. The sockets I need. I went to the store to buy the sockets that I need. Right here. I went to the store to buy these sockets right here. Mr. Kotuman. I went to the store to buy these sockets. I know that I need how many sockets? I need one socket. I need two DC to DC sockets. I need another socket here. I need I need another socket, the inverter sockets. Now, what they are saying is, for this area here, for this PV model, for the socket from my PV model to my junction box, I should know now the maximum current is 12.6. So when I go to buy this socket, I'm going to check the socket, look at the manufacturer rating on that socket or the sheet or whatever to know that this is the max. I'm not going to go look for a socket that is less than 10.5 or less than 12.6. The reason why I do that is because if for any reason the sun go over its normal pitch, so the sun shines so high, it's so high, my sockets will be able to withstand the pressure. Is that clear?
Excuse me.
Mm-hmm.
In this system, what is the front door and the socket?
The socket is the connection point between these here. You see this? These right here. These are the sockets. Yes, you have. From the DC to DC connect, we got two sockets. Even though we have 20 panels over here, 2, 4, 6, 8, 10, 12, 14, 16. We have 16 panels over here, but we only have two sockets going to our junction box. Did you get it?
The line connecting the east to the back.
Huh?
The line is connecting the array
Yes.
So the joiner box.
Yes.
Yeah, our socket.
That's your socket. And they are saying you must be able to know the maximum. That's what we're trying to do. You get them. You made me feel better. It seems that you just grasp the whole concept. You see, so what we're trying to know here is to know the maximum right here. The PV source and PV output socket maximum current. You want to know this. So that although those connector that is going to become a socket to connect to that connecting to our box there, you want to know, you want to be able to do the math, or you want to know the maximum current, the maximum the socket maximum current. You want to know the max. They will give you on the PV model. They don't give you the max here. They'll just tell you the STC rating power tolerance here is plus 5 watts. That's what they're saying. That's the power tolerance. So they're saying all of these here, you add 5 watts to them, it will tell you the power tolerance. That's what they're saying. You add 5 watts to all of these, that's the power tolerance. So since you have 380 watts, you add 5 watts to 380 watts, it becomes 385 watts. That's the power tolerance. But we don't use that formula. What we use the NEC requirement, NEC, which is, we use that 1.25. So that's why you have to check for the socket. They gave you the minimum socket here already. I know my minimum socket is 10.05. Once I look on the data sheet of that model, I see that my short socket current minimum, the short socket current minimum amps is 10.05. I'm going to take that 10.05 and multiply it by 1.25 to give me the max. So when I'm buying my sockets for my connections, I know to check for the maximum. I know now I'm going to check for the maximum. But most of the time, these PV models, some of them do come with the cable. They come with the socket already. Most of the DC section, it comes with that already. But just to be sure, you must know this practically, how to calculate your max, because they gave you already the short socket. The short socket here is 10.10. My short socket is 10.14. My short socket at 395 watts is 10.19. I take 10.19, 10.19, and multiply it by 1.25. That is 2.7. 12.7. So that is the max. So when I going to buy I had to buy my sockets for my runs, I'm going to check the max. I want to know the max. I cannot buy something that is even less than 10.19. Is that clear?
Yeah.
So that is very important, but we'll go along.
And you were saying something, the tolerance.
The tolerance I'm talking about, you need to know the maximum so that in case there is a continuous. You remember when I was reading, I was using the word continuous?
Yeah, yes.
So they were saying is that, okay, we know the temperature of our area. We know that in Liberia, this is the temperature. The model here will tell you what the temperature. Let me tell you what the temperature of the model is. They will tell you the temperature. Let me see right here. Let me look at the data sheet. Electrical characteristics, temperature coefficients. They tell you the temperature right here. The temperature coefficients of the ISC plus 0.04. Temperature coefficients. They tell you the temperature coefficient. You know the temperature coefficient of your model. You do. But we're saying is the reason why they use the word continuance is because you cannot determine what on a certain day the sun could shine so crazily that it will go above what it have always is. So when in that scenarios, your conductor will be able to handle that maximum current. You got it? If I was to size, do my sizing, if I was to size my model here, if I was to size my socket, this socket, let's say for example, all right, let me look at the PV source sockets. If I was to size this PV source socket here at 10.5, let's assume I size all of these sockets here as at 10.5. That is the minimum. I say 10.5. Everything, all this socket here is sized as 10.5. If I was to size this socket by the given minimum, they give you the minimum right here. The manufacturer is very smart. They don't give you the maximum because they cannot predict what's going to happen if the sun goes so high. They tell you the minimum here for the short socket, the ISC, is 10.5. It is my duty to know the maximum. And how do I find my maximum? I multiply this 10.05 by 1.25 to give me my maximum. So when I'm sizing my socket, I'm going to size my socket at the max. So should in case for any reason whatsoever, there is a high saturation of power coming down from the sun, I'll have my socket will be able to withstand that high pressure. All right, when you're walking and the sun is too high, what do you do? If there's a sunlight in your eye, and you usually put your hand over your eye?
Yeah.
Okay. Do you always have to put your hand over your eye when you're walking?
No.
It only happens when the sun ray is too high, you know so? If you want to see something, even when I'm driving, sometimes you have the sun ray coming, not all the time, but sometimes you're driving something, the sun reflection coming to your car. You put your hand over your eye, sometimes you cover your eye, or you put the sun visor and so forth. So they put that sun visor there just for in case that happens.
Okay, Brother.
Yes.
There be a battle when the 12.6 socket when the baby man they come at 12.6 as supposed to get 12.6, they are going to purchase it. And they are having to find the 12.7, and I you say also.
Well, that's that it's a 12.6. You found the 12.7?
Yeah. Maximum.
Yeah, it's not advisable. I show you have a range. If it's 12.6, 12.7 will work. It will work because if you notice here, they already told you that you add 5. They already told you the maximum performance standard STC condition, the STC power of this is +5. So yes, you can add at least 1 point to it because you notice that this solar panel here you add 5 to it, that will be the maximum tolerance, the maximum performance. So even though it's rated as 35 at 380, but you add 5 to this will be 385. This is rated at 385. You add 5 will be 390. So yes, what you're saying in short, I can use this here for this, but I cannot take this 300. I can take the 395 and use it for the 380. Okay?
All right.
You got it? Is that area made clear, man? I will have the guy explain it practically tomorrow when he gets there because I got to continue. Look right here. They say right here, as a matter of fact, they say the permitted model temperature of continuous duty. Look right here. It's even say on the data sheet. It's written right there. Safety class number 2, the permitted model temperature on continuous duty is below 45 degrees up to plus 85 degrees. You got it? So what if the sun shine up to 90 degrees or 95 degrees? And you went and used the minimum socket for your calculation for your minimum. So when you go up to a high, you're gonna have a drop. That's why they're saying to avoid the drop. You're gonna have a drop because it may even shut down the system. It may even shut down the system. So that's why it's good to find your maximum current socket, the maximum current and socket current. It's important to find that. Are we clear on that area? All right. So if I'm going to ask you a question, let me ask you guys a question. If I was to, I'm going to give you a, let me give you guys a quick, I'm going to find a, hold on, I'm going to find the data sheet for a model. Hold on, I'm going to give you the data sheet of a model. Hold on 1 second. And you guys will tell me what would be, yeah. Oh my God. Even a matter of fact that some PV model already says it on the model. It says it right there, like this model right here. It tell you what the maximum is already, the maximum power current, the maximum short circuit. Okay, the short circuit, the maximum system voltage, the maximum series, or they don't tell you the max. All right, so I'm gonna give you this here. You guys gonna do this for me. I want you to do a little bit of assignment, get your basics since I got sleep in the class. All right, is Fico sleeping right there?
No. Wow.
All right, guys, can you see my screen?
Yes, yes.
All right, that's a sun power 100 watts model. I want you guys to find 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 the maximum current socket for that model.
What is the minimum?
That's why I posted that for you right here. Or what's the thing I just put right here on the screen?
Go back.
Can you see it now?
Yeah.
I want you guys to calculate to find the minimum. This is very beautiful. They even tell you what kind of wire to use. 12 AWG at 4 mm insulated a 90-degree sensor. They tell you right there on the back of the on the nameplate of the panel. It tells you right there.
Yeah, the minimum I see here is 0.20. So
What?
the minimum is 0.20, the maximum is 7.8.
The minimum is 6.1.
7.20.
What's the maximum?
7.8.
Okay, you guys, what you guys got? All right, excellent. So that's That's exactly what I give you one more. Test it one quick for me. You see this one?
Yeah,
So the model type, JKM, the model number, the maximum power is 290 watts. The power tolerance at 3%. The maximum power voltage, VPM. The maximum power current, the IMP. The open socket voltage, the VOC. The short circuit current, the ISC, which is 9.61 amps. Tell me what would be the maximum current.
12.0. So we got 12.0.
We got 12.0.
Yeah, maximum 12.0.
12.0 amp, that's your max. All right, guys. So you guys got the concept. That's why you got the concept now. Good. You got it now. That's the concept. That's the whole part of this whole learning process. I'm gonna copy the concept now. All right, let me try and summarize this ending so we can move forward. You got the concept. Now we were just talking about the socket. Now we're going to talk about inverter. Okay? The power electronic socket, maximum current. Inverter and DC to DC converter cannot produce more current than their range, the ratings. DC to DC converter socket maximum current. Rated continuous output current specified by manufacturer. Inverter output socket maximum current. Now I want to see what the inverter maximum output current. I'm going to go to the inverter now. The NEC section 690.8 define maximum socket current or maximum current for DC to DC converter source socket as the DC to DC continuous output current ratings as specified by the manufacturer for DC to DC converter output socket. The maximum current is defined as a sum of parallel connected DC to DC converter source socket current. Since the DC to DC converter will not produce more current than their ratings, the additional 1.25 factor is not required. They will not produce more than they is not required. Okay? Because they has a rating, they cannot exceed that. It's not required. Let me move forward. For example, in a system with two DC to DC converter source sockets, the maximum socket current of each will be the rated continuous output current of the converter, 15 amps for this example. The maximum socket current for the PV output socket consisting of those two PV source sockets in parallel would be the sum of both source sockets, 30 amps. Likewise, if there were 4 DC to DC source sockets connected in parallel, the PV output socket maximum socket current would be 60 amps. What they are saying is, if you are using a DC to DC converter from the manufacturer already factored in the 1.25. You got it? The DC to DC converter, the manufacturer already factored that in. So once you connect a DC to DC converter on a model, it gives it a standard rating. So for example, if the rating is 15 amps, it's 15 amps. It's not going to exceed, that's 15 amps. It's not going to pass that. So that's one of the advantages of having a converter versus not having the converter. When you don't have the converter, then you have to determine the max. You have to determine the max. Now let's go. We're not going to be using converter a lot. So let me move on to something more. Sizing conductor for PV system continuous duty. Sockets are considered continuous when maximum current can flow for 3 hours or more. Hello? PV system DC AC socket are continuous. Continual operations, more heat produced, additional 1.25 safe factor adjustment required. PV source or output socket adjustment for continuous duty equal PV max, PV maximum socket current times 1.25. The I equal the ISC times 1.25 times 1.25. Power electric socket adjustment for continuous duty equals socket max current times 1.25. This is very sweet. Now, the NEC section 690.8 require conductor to be sized based on a calculated continuous current for each socket. The current in PV systems are considered continuous because they will be sustained for 3 hours or more at peak output, meeting the NEC definition of continuous. They leave it open. They use it. My son like to say a word infinity. You know what I mean? My little boy like that word for infinity. So they leave it open. They didn't say, okay, we can guess the height of the sun. They leave it like that. Sockets that will be operating on a continuous duty must have an additional 1.25 factors of safety applies to protect them from overload during continuous use. This is separate from the previously discussed irradiant factors and is sometimes referred to as the 80% rule, as 1.25 is a reciprocal of 80%. 80% operation equals 1 divided by 0.80 equal 1 times 1.25. When this correction factor is applied, the conductor will carry no more current than 80% of its rated ampacity. I will explain it further. I'm just enjoying the reading. So for PV source sockets and output sockets, the continuous current equipped equals the maximum current times 1.25. This is the same as the ISC times 1.25 times 1.25. The total factor are sometimes combined and stated as the ISC times 1.56. Continue. So let's go back. Let's go back here. All they are saying here is when we calculate and find our 1.25, you remember how we calculate to find the 1.25 of our PV socket? Do you remember that?
Yeah.
So this is, all right. Okay. Now, they're saying, let me go back here. We already did know how to find the max for the model. Then we know that already for this socket. We know how to find this socket right here. That's what we're doing. Remember?
Yes.
Okay, I'm not going to go use the inverter part. Okay, this is what we already know how to find the max for that. We're trying to find the max for these ones here, the one that goes down here. You got it?
Yes.
Okay, for these other sockets, they are saying whatever max we find over here, we are going to multiply that max by 1.25 to find the max for these other sockets down here. Is that explicit? So let's say, for example, in our PV model, I showed you the 385 watts. The open socket was 10.05. Remember? 10.05. We multiplied that and we got 12.6, didn't we? Now we're going to take that 12.6, we're going to multiply that by 1.25, and now we got 15.8. So it changes. That is why when you look here, you notice that the width of the socket change coming to the DC disconnect. Do you notice that the width changes? If you look at the diagram over here, the wiring is look smaller than the wiring that come down here to your inverter. Did you notice that?
Yes.
So they are saying from your disconnect right here, from this coming to your disconnect to your inverter, this PV socket right here, we have to. That's why you know. Look at it. Look at the size. You see the size, the wire size. Are they the same?
No.
Okay. So they are saying that is 15.8 amps. This is 12.6 amps. This is 15.8 amps. That's what they're saying. You got it now? We did a calculation to find these sockets out here. We look at the short socket of the model here, which were given to me. I used this right here. I look at the data sheet of the PV model, 380 watts model. The short socket, which they gave it to me, they didn't give me the max, but they just gave me the short socket. They will always give you the short socket. The short socket is 10.05. I took this 10.05, I multiply it by 1.25, I got 12.6. Now, that enabled me to know what socket I need for this over here for my model to my compounder box. I know what size socket I need. Now, to determine the socket I'm going to use from my DC compounder box to my inverter, the DC side, not the AC side. We stay on the DC. From my compounder box to my inverter, we need a more bigger, so we have to multiply the 12.6 by 1.25 to find what connection we're going to use, what socket we're going to use between here. How many of you have seen a pipe, a plumbing connection when they do the plumbing connection in the house? How many of you have seen that? Okay. When a plumber let me just use that scenario. When my first training program I did was residential plumbing. When a plumber does the pipe configuration on the ground, for your sink, he used the 2-inch pipe. Now that 2-inch pipe, he has to have a reducer to reduce that 2-inch pipe to come down to connect to the 4-inch pipe that connects to the commode. The commode is not 2-inch, so you're going to reduce it. He will start with a commode, which would be a 4-inch pipe from the separator going into the house. That's a 4-inch pipe. Then he will reduce that pipe from a 4-inch to a 2-inch, which goes to your face basin and your shower and your bathtub. So I'm just using that scenario that if you notice here is that all of this current here going to run to this inverter once this disconnect is open. Do we got it?
Yeah.
So since all of the current here from the compounder box going to run to the inverter here, they must have a socket here that can handle that pressure.
Yeah.
You got it? I think when we continue, you guys will get it. And then we will go over again. Now let's see where we were. All right, guys. You guys wanted to stop here, and tomorrow we continue this lesson.
Okay.
Okay. So we're gonna stop here. 1, 2, 3, 4, 5, 6. So it's about 7 p.m. over there. All right. So 6 to 7. So we're gonna stop here, and we'll continue this lesson tomorrow. Okay.
All right.
We stop on page number 12. We're going to continue tomorrow. Tomorrow we'll continue. We'll talk about conditions of use, higher temperature, reduced conductor ampacity. We're going to talk about the device terminal compatibility. We're going to talk about the voltage and so forth tomorrow. Okay, guys? All right.
Hello?
Yes.
Hello?
Yeah, go ahead. My son is coming. I don't want him to throw the light down. Go ahead.
Yeah, I would like to use my low AA camera.
Huh?
WhatsApp. I need the group WhatsApp.
Oh, okay, great. I will.
I sent to you by WhatsApp.
All right.
You WhatsApp are using for my abilities.
All right, great. Are you there?
Email that.
All right.
Brother,
Yes.
I have downloaded the video.
All right, guys.
Class 2 or class 12?
Yeah, class will be the same. I gotta go. My son, I want to play with him.
I got